A very good day to all. My name is Sean Kai, and today me and my groupmates will be presenting our project assignment for course KM30903. So, for introduction, a mechanism is an interaction of rigid parts which are linked by joints in order to transmit, control, constrain, or translate motions and/or force from one part to the other. Mechanisms are used in machines as they can achieve their required functions. Since a machine could need to do anything that can work, it can range from a simple, like a can opener, to something complex like a telescope that can be used in observatory. In this project assignment, we will be looking into a specific mechanism that can be found in most machines, which is called quick return mechanism. A quick return mechanism is a mechanical assembly to create a reciprocating motion which is designed to reduce the ideal time required to return the stroke. It is a four-bar mechanism consisting of a fixed link crank, pin sliding in a slot, and a sliding pair. An electric motor runs the pinion at a uniform speed, which then allows the pinion to transmit its motion to the gear. Then the gear will have a pin on its surface which can be confined to slide inside the slot of the crank. At the point where the gear nears at full revolution, the arm will achieve its farthest position and then comes back to its initial position at a faster rate, thus its name. It has many applications such as shaper, power-driven saw, mechanical actuator, and many more. So this quick return, so figure 1 shows the examples of a quick return mechanism. And this quick return mechanism can be also modeled after the crane and slider or arm, and this is present in its appearances and function. However, the crank is usually hand powered and the arm has the same rate throughout the entire revolution, whereas the arm of the quick return mechanisms return at a faster rate. The quick return allows for the arm to function with less energy during the cut than the initial cycle of the disc. So according to the mechanical jungle, there are three types of quick return mechanisms, which are A, the hydraulic drive, B, crank and slotted link mechanism, and C, Whitworth mechanism. We were tasked to design a quick return mechanism for a crusher machine that consists of components like the DC motors, gears, crank, and accessories. With this task in mind, we decided to implement the Whitworth mechanism for this crusher machine specifically. So for complete understanding of any mechanism in general, the kinematic and dynamic analysis will play a significant role where they will provide valuable information such as the position, velocity, acceleration, and acceleration of each link, as well as the total force acting on the mechanisms. So according to a report written by Moncova and Monka, the three methods were used for the kinematic analysis for the quick return mechanisms. The authors concluded that the computer-aided method is more accurate and faster compared to the rest. Chowdhury and Saha, back in 26, had used maximal recursiveness of a dynamic equation for the evaluation of bearing force in their research report, in which the authors optimized vibration and improved the balancing of four-bar mechanisms. And another research report written by Urkaya and Su, a dynamic analysis of the slider crank mechanisms, and one of them being the simpler slider crank, and the other being a more modified slider crank, where an additional link is added between the connecting rod and the crank pin, which is distinct from your conventional slider crank mechanisms. The authors concluded that the force output is far greater in the modified slider crank mechanisms. Russell and Sohei had created a method for designing a slider crank mechanism to achieve a multi-phase motion generation application, which is typically accomplished by adjustable planar 4-bar motion generator. And finally, Touchbox and Usni has generated a dynamic stability of the flexing connecting rod of a slider crank mechanism where it is operated at a high speed and rapid response. The authors also said that it was necessary in order to reduce the mass to the smallest possible value in order to minimize the inertia effect. As a result of this, some members in the mechanisms are subjected to elastic deformation if the mass of inertia was reduced without considering the elastic behavior. As well, the mechanism developed instability of parameters which resulted in the reduction of the efficiency and reliability of the mechanism to an undesirable degree. Finally, the authors also concluded that the large amplitudes of axial load is responsible for the occurrence of the infinite regions of instabilities and is also due to the larger axial load. Kinematic analysis mainly divides into position, velocity, and acceleration analysis, while the dynamic analysis is the essential requirement to understand the dynamic behavior of a mechanism, which is also called force analysis, in which we have to consider all the forces and mass of each link. So this is the example of a vector representation of the Whitworth quick return mechanisms, where from this figure, it can be broken up into multiple vectors with two loops. Utilizing these two loops, the following section will go through the kinematic analysis of the Whitworth quick return mechanisms. So first one will be position analysis. So for the Whitworth quick return mechanism shown in figure 1, the displacement analysis can be formulated by the following loop closure equations written here by 1A and 1B, where it's related to the length of the members. And using these complex numbers, equation 1 can become, it's written here, from 2A and 2B, where the link lengths R1, R2, R5, and R7, and the angular positions theta 1, theta 6, and theta 7 are constant. Angular position theta 2 is an independent variable, whereas the angular positions theta 3, theta 8, theta 4, and theta 5 are dependent variables. Looking back at figure 1, it can be seen that theta 8 is equal to theta 3, which is also equal to theta 4, and R4 is equal to R3 plus R8. Substituting and rearranging equation 2, which is here, and to have all of the unknowns on the right hand side and all the knowns on the right hand side will give formula 3a and 3b here. Okay, looking at back at equation 3, it can be seen that equation 3a has two unknowns and equation 3b has three unknowns. Utilizing Euler's equation, where e powered by I theta is equals to cos theta plus I sin theta. Equation 3a can be broken up into two equations, one consisting of the real numbers and the other consisting of the imaginary numbers, written here for 4a and 4b here. Squaring equations 4, adding them together and simplify will give us equation 5 here. And dividing equation 4b by equation 4a and simplifies it will give us equation 6 here for theta 4. Okay, knowing theta 4, equation 3b can now only have two unknowns and will become here, written here in equation 7. Since the right hand side of the equation 7 is constant, we will let Re powered by I theta equals to R4 e powered by I theta 4 minus R7 e power I theta 7 and use it in the rest of the calculations. So breaking down equation 7 here up into a total of real and imaginary parts will give us equation 8a and 8b here. So solving for both equations A will give our R6 written here for equation 9a and 9b here. Whereby equation 9a will be used when cos theta 6 will be greater than 0, and equation 9b is used when cos theta 6 is equal to 0. Substituting equation 9a into equation b will give us formula equation 10 here. Solving for theta 5, we will get equation 11a and 11b here. Knowing all the angular position and lengths of R6, we can find the position of the output slider length 6 using the formula here written in equation 12, where P6 is equals to R4 plus R5. So next up will be velocity analysis. For the Whitworth quick return mechanism as shown in figure 1, the velocity analysis can be formulated by taking the time derivative of the loop closed equations. Taking the time derivative of equation 2 will give us equation 13a and 13b here. Equation 13 can be simplified since r prime 1 equals to r prime 2, which also equals to r prime 4 and equals to r prime 5, which finally will be equal to 0. These links are assumed to be rigid members that may not elongate, whereas W1 equals to 0, whereas link 1 is a rigid link that is unable to rotate. W6 is equals to W7, which is also equals to 0, and theta 6 will be equal to 0, as links 7 and 6 and 7 are assumed to be non-rotating imaginary members, and R prime 7 will be equal to 0 due to the fact that output slider 6 is assumed to remain on the ground at all times. Applying these simplifications, we will get equation 14a and 14b here. Equation 14a will have two unknowns, whereas for equation 4b will have three unknowns. Breaking up equation 14a into imaginary and real parts while solving each for r prime 3 and setting them equal to each other and solving it for w4, we will give us equation 15 here. R prime 3 can be found by plugging the found w4 above just now, this one, into either the imaginary or real equation for equation 14a. With the known w4, equation 14b will now only have two unknowns, r prime 6 and w5. Breaking up into its real and imaginary parts, we will have equation 16a and 16b here. Solving for equation 16b with w5, we will get equation 17 here. R prime 6 can now be found by plugging the found W5 and W4 into equation 16a here. We can find the velocity of the output slider link 6, which using the formula 18 here, where V6 is equals to R prime 6 plus R prime 7. And breaking equation 18 above into its x and y components, we will find that equations from equation 19a and 19b here. And lastly will be the acceleration analysis. For the Whitworth quick return mechanism shown in figure 1, the acceleration analysis can be formulated by taking the second time derivative of the loop closure equations, or by taking the first time derivative of equation 14, which gives us equation 20a and 20b here. Equations 20 can be simplified further, since that r prime 2 is equals to r prime 4 equals to r prime 5, which is also equal to 0, as links 2, 4, and 5 are assumed to be rigid links that are unable to elongate. Breaking down equation 20a into real and imaginary parts will give us equations 21a and 21b here. Solving equations for 21 for R3 and setting them equal to each other and solving for alpha 4 will give us equation 22 here. R double prime 3 can now be found by plugging in the found value of alpha 4 into equation 21a. With the known alpha 4, equations 20b now will only have two unknowns, R double prime 6 and alpha a. Breaking up into real imaginary parts will give us equations 23a and equations 23b here. Solving for equations 22b for alpha a, we will find that from equations 24 here. We can now find that r double prime 6 by plugging in the value of alpha 5 into equations 23a. The acceleration of the output slider link 6 can now be found with the value from using equation 25 here, where acceleration 6 is equals to r double prime 6 plus r double prime 7. While further breaking down equation 25 here into its x and y components, we will find equations 26a and 26b here. So for the dynamic analysis of the Whitworth quick return mechanism, utilizing the previous analysis for position, velocity, and acceleration along with the inertia properties such as mass and mass of moment of inertia for each moving body, we can now be able to perform force analysis of the Whitworth quick return mechanisms. This is done by pulling apart the Whitworth quick return mechanisms and determining the static force equation of each member. This model would neglect friction forces. When the force equations for all members have been found, a matrix equation can be formulated and the required torque input for wanted force output of the output slider link 6 can be found. That is all from me. Thank you.
Yes, hi, my name is Stanley, and I'll continue the presentation and I will discuss about the force on each member, which each link in this design. So we have this Whitworth quick return mechanism as shown in this figure. So there's few link in here. This first is a second, and third or fourth or sixth. So we have about six link in this our design, and where I can say the link of link two is the key of all this design. So the force that will transmit to link 3, 4, 5, 6 is all transmitted from link 2, and from link 2 is where we input our required tool to produce our needed load force. This is located at link 6. So here in link 2, we can calculate the force with this equation, where we'll see the equation is needed mass, and then the forces is linked with the gravity, center of gravity, and also the tool, this the driving tool, which the tools supply input tool. Okay, so next we will go to link 3, and link 3 is transmitted from link 2. The force is transmitted from link 2, and then it will go to link 4. And we have obtained the equation from our reference. So we have link 4, link 5, and link 6. All they have the separated equation, but it's all about similar, just changing the force that has been transmitted from link 3 and then transmitted to link 4. That's all we are changing. At the same time, we also change the center of gravity, which is depend which link we in calculation. So we can jump to the result and discussion. Here our idea is how we can determine our needed input tool to produce the load force needed in the output slider. So here, for example, we have decided our output slider, the load force needed to be 100 Newton. The negative sign or positive sign is always the is always represent the direction only. So from the equation that we have discussed in the kinetic analysis, the acceleration, the velocity analysis, first of all, we have to set our few parameter we have to set. The first one is the length of the link. So we have set the length of the link for each of the link. So for example, we have set R1 equal to 2.5, R2 equal to 1 cm. So after we have set all these parameter, we look back at the equation, and we also need the mass. So in the mass, we also needed to calculate for the velocity. Acceleration analysis is required. So this where we need to set ourselves and run through a few time of calculation. So the length and the mass is used for the velocity and the acceleration analysis lah. And we have also need to set the center of gravity that which will be used in the finding the force for each link. And then was the angular velocity of link 2, which is very important, that all the mechanism working is based on this link 2. So after we have the angular velocity of link 2, which produced from the input tool, so it will transmit the velocity or the force to another link. So from there we can calculate one by one until we solve at the link 6, which is the output slider. So here, after we have run through our calculation and all the parameter, we have substitute all the parameter in our equation. We have, as a result, we get the velocity output of the slider is 0.14 meter per second, and then the acceleration is 3.19 meter cube per second. So also we have determined the maximum and minimum position of the output slider, which maximum it can go to 0.05 meter, and then the minimum it will return to 0.002 meter also. So this example of the slider velocity versus time, and we can see the difference between the return and outgoing speed. I mean not speed, the time consumed for the velocity go through. Okay, and then we have calculated the force with the which I have introduced you about how we calculate the force in each link. So we and plug in all the parameter, and then we calculate this force from the input to tool, which acts in x direction and in y direction. But the important here is we will have to look in the F16, which is the transmitted force to the slider, output slider, which will we get about 100, is more than 100 Newton. Here is 105 Newton, which is almost achieve what we needed as output force for the output slider. So in conclusion, we also managed to design with all the equation from the uh, from what we have referred to. So it's very happy and feel benefit to doing this assignment, which this assignment is about quick return mechanism design and using the analysis type, which we have go through the kinetic analysis and dynamic analysis. From the equation, we do our design, which we have how to what parameter that we have to set by ourselves, and then what kind of parameter that needed to find out to determine, and that's it. And then to be easy, we can also use the computer programs, which is benefit and faster the calculation process. But here we doing it soft calculate manually, and finally we have find out the output force needed, and then this assignment is very benefit us with the terminology of machine, and that's it from me. Thank you.